Yeah. So today we'll start with dimensionality reduction. So similar to feature elimination technique, uh, dimensionality reduction also reduces the feature space. Like in the previous approach in which we recursive feature elimination, we saw how I mean like 10 features were reduced to 4 features here, right? Top 4 features if you want to take. Here we saw top 4 features which are BMI, S1, S2 and S3. Dimensional reduction does a similar thing, but here what happens is it recursively removes one after the other, whereas dimensionality reduction you can select which feature. Essentially, it is the opposite of elimination, because here you are eliminating, here you are selecting. You will get some scores for similar to mutual information. Here you will get some scores, and based on those scores, you decide which features do you want to select. Now, what dimensionality reduction is? Because I mean, what this approach is. So, dimensionality reduction means that we have, let's say, n number of features, a lot of features, and we want to reduce it. Why do we want to reduce it? We have talked about it in the first session itself. Because when you have a large number of features, it results in overfitting, and secondly, it also reduces the training time. I mean, it increases the training time, it or reduces the training performance, right? So these are the two primary reasons why we want to do dimensionality reduction. And here, by dimensionality reduction, I meant principal component analysis, which is PCA. So PCA is one of the dimensionality reduction techniques. All these other approaches are also, you can say, as dimensionality reduction, because they are reducing dimensionality. But generally, when someone says I am using a dimensionality reduction algorithm, they mean that they are using PCA, or principal component analysis. Now, what is principal component analysis? Principal component analysis is given some feature, you project them to some higher dimension or other dimension. Like for example, you are given XY coordinate in some dimension. You project it to some other dimension such that you can understand, I mean, so that most of the information in your data is preserved within lesser number of dimensions. Let's say we have a 3D data, right? Three-dimensional data, where X, Y, and Z are given. Like for example, a color photo is actually a three-dimensional thing, wherein X, Y coordinates are pixels, and the third coordinate is the color, whether it is red, blue, or green, right? So this is a three-dimensional thing, but sometimes we need to make it a two-dimensional thing without losing any important information. That is what principal component analysis is doing. From a higher dimension, let's say 100 dimension, it will reduce it to the smaller dimension without losing, I mean, without, obviously, to lose some information. It cannot preserve all the information that is there, but it will try to keep as much as information as it can. So in so that I mean, how it is said is that generally in data, we have two things. One is the mean, and the second is the variance, right? So variance is how widely the data is distributed. Variance or standard deviation, this statistical measure tell you how dispersed the data is. Now, when we convert from, let's say, 10 dimension to 2 dimension, it is for sure that we will lose some of the variance. We will not be able to capture the complete variance. But what we want to do is, if we can at least capture 95% of the variance in the 2 dimensions or 3 dimension, that is the target of PCA. So PCA tries to reduce some higher dimension, let's say from 10 dimensions to 3 dimension, 2 dimension, while preserving as much as information as it can. Okay, now what it is said is that digit dataset is an image classification problem, right? So images usually have pixels. So let's say we have a square, like a chessboard you can think of, where is 8 cross 8, and within that some pixels are like white, some pixels are black. Like for example, when you look at your calculator, right? So how do you read a number 8? Because some of the cells are black and the background is always white, right? Similarly, in case of our images also, when some pixels, now for example, here we are seeing black because actually we are not seeing the grid, but internally in the screen there are some grids, or like a chessboard, and some things are black and some things are by default white, right? So like for example, here this letter R is coming out because some pixels are made black. That is why you can read this as R, and other pixels are white or having an intensity of 255. This is having an intensity of 0, black. So that is how letters and alphabets are formed. And similar to this, like this digit data set, if we look at this, let us have a look at this digit data set. Okay, now you see it is a it has, if you look at x dot shape, it is saying 1797 cross 64. Why it is saying 64? Actually, image is 8 cross 8. It is never a one dimensional thing. But what they have done is they have flattened it. Now, anything like, for example, a 2 cross, let me give you an example. Let's say there is a matrix which is like 2, 3, 4, 5. So this is a 2 cross 2 matrix, right? 2 cross 2 matrix. Now you can convert this into a 1 cross 4 matrix also. How? If I just write 2, 3, 4, 5, so it is a one dimensional matrix which represents the same thing, right? This is a two dimensional thing, this is the same one dimensional representation of this two dimensional thing. Now these images that they have in this data set are actually 8 cross 8, which is actually 8 cross 8 means 64, right? So they have converted them into 1 cross 64 array elements, and they are putting them into this order. Like, if I just show you how X looks like, let's say X first row, let us take first. See, so it has 64 data points. So what it is saying is this has a 0. 0 means it is a black cell. It means it's a black cell. Why? This means it's a gray cell, like somewhere between 0 and something, not very high, not very low. So something like this, right? So 0 means black, any other number is like a gray, whereas like maximum value should be 255. So are there any 255, or they are using 16-bit? I don't know if they are using 16-bit in this, then maximum value will be 16. I think they are using 16-bit, 4-bit numbers. So the maximum value will be 16, minimum value is 0. So when you see a 16, it means that there is a white cell. If it is a 0, then it is a black cell. Okay. Now see, as I told you, right, there is pixel 0, 0, 0, 1, 0, 2, and like this it will be 8, 8. So that is where all these 64 features are there, feature names, right? Because they have flattened this image into a single single array, and they are using it, each of these is a pixel entity which is a feature. Now the problem is like pixel from 0, 0 till 7, 7, right? 0 to 7, like these are like 8, and 8 cross 8 is like 64. So now the thing is, and if you look at y is saying whether some number is a 0 or a 1 or 2 or something like that, right? So if I just let me see, so like we were looking at x0, like x0 is actually this number, and if we look at corresponding y0 is 0. So it means it represents the number 0. Like for example, y1 means 1, and if we look at x1, it is looking like this. Now this pixel information represent the letter 1. So there are in total 64 features here, but the problem again, we want to reduce the dimensionality, right? We want to do it with less number of features. So from these pixels, we want to identify which pixels are more important, which I should look at while deciding whether, while classifying some image as a number 0. So this is actually image classification problem, wherein you are shown an image to the computer, and it is saying what is the number, whether it is 1, 2, 3, 4, 5, 6, 7, 8, 9 till 9. Now these represents all the pixels, and it is predicting any number from 0 to 9. If we look at all of y, you will, I think, let's write list of y. I think it will print everything if I just write list. See, so all the numbers are between 0 and 9, right? So nothing beyond that. So it is a multi-class classification problem wherein So in the first one, you saw it's a binary classification problem where the target is someone has cancer or not. This is a multi-class classification problem wherein your output can be multiple classes from 0 to 9. So in this kind of problem where you have multi-class classification and there's a lot of features like more than 50, 60 features or something like that, then you should always look at dimensionality reduction before doing anything else. Now, dimensionality reduction is defined inside scikit-learn decomposition method, which is a PCA library. You are saying what are the total number of components here? It is like 64, right? So if we want to keep all the 64, then you can set your components as 64 and you want to just run it, right? So what it is saying is for each of these feature, how much of the variance is, like for example in mutual information we saw how much percentage of the total target variable information has each feature has. Similarly here we are saying out of this each feature how much of the data variance is captured by this, right? Now if we want to look at only top 3, we'll say that you just do a same thing. Here just n components is 64, you reduce the n components to 3 and you just run same thing pca.feed transform and you see the shape is now reduced to 3. And if we look at explained variance, you see that first, if we say I want to take 3, first is having 0.14 variance, second is having 0.13 variance, and this is having 0.11 variance, right? Similar to this only, right? Similar to this. This is also meaning the same thing, 0.11. But you see, like what this number means is 0.14. This is 0.13. This is 0.117. So like this, if you look at this, this will be like 0.08. This will be like 0.057. This will be 0.04. This will be 0.04 again, like this, right? But if you scroll down, like from here onwards, where there is 0 from, I mean like from this, where is E minus 03. So this is like 0.009. So till this, I think there is significant contribution to the variance. From this onwards, you can discard. So if you look at this, how much will be this? 1, 2, 3, 4. 4 into 4 is 16 and then 3, 19. So if I use 19, I should get decent amount of variance. Like if you sum all of them, this is a list or what? This is a list or numpy. This is a numpy, okay? So these are the things. Now if we do np numpy is imported, import numpy as np and np.sum pca.explain. So you see 88%. So when you are doing a sum, it means 88% of the total data variance is captured by this many features. Remaining so many features are having only 12% of the data. So ideally, the while applying PCA, the thumb rule is you should go till your variance becomes 90. At least 90 you should reach. Okay. So here 19 may not be the right thing. So let us try 22 and see what is the value. See, with 22 we are getting 91. So I think this should be enough. So what we have done is we have reduced from 64 to 22, and while capturing 91% or 91% of the data variance, right? So which is decent enough. Yes. Right? So this is where principal component analysis helps. I mean, once this is done, if you still feel that you want to do some feature selection after dimensionality reduction, you can apply a mutual information or something on top of dimensionality reduction. Okay. So why I have not printed? So someone may ask that in the first 2 cases we printed what are the top 4 feature names, right? So like these are the top 4 features here. Here we printed that these are the top 4 features or top K features. But here we are not printing the top K features. Why? The reason is this pixel 00 is no longer pixel 00. It is converted to something else now. It is converted to some other, it does some transformation internally. It converts it into something else. So the feature that you will get now after this, like this 1797 comma 22,
Hmm.
this will not be the same 22 from here. It will be some other data. It modifies the data itself. Like for example, if you look at let us say if you look at x0 from here, and if I let's say, okay, this is after this thing, have I done? No, this is normal x. Now there is a x PCA also, right? So let us try x PCA of 0. See, the numbers are different, right? So it doesn't maintain those numbers. It has 64 entries, it will have
Okay.
22 entries, and also the numbers are different because it transforms the data so that it can preserve the information and all, right? So it is little different from the other approaches that we studied. Here what happened was you will get the same features. Only thing is that some columns will be dropped. Similar to this also, here you will get the same data. Only the 4 columns which are selected by this, those data will stay. Other columns will be discarded. Here you are selecting. Here you are getting 22 features, but which 22 you don't know. I mean, it is transforming the data to some other things, not directly mapping to the features that you have here. Okay, got this point, right?
Yes.
Okay. Cool. So these are the three feature engineering techniques. There are 3 more. I will cover those now. So now this is we are coming to part 2 of feature engineering. This is also very important. This will actually, I mean, this is actually one of the, I mean, this is one of the techniques I use in my while doing data science feature engineering. Uh, this is a feature importance, right? Something, I mean, there are many ways of computing feature importance. We saw some of the techniques previously, but based on my experience, I have seen that this tree based method helps me a lot while designing data science solutions and all. Like for example, we are taking a wine dataset, which is a multi-class classification problem. You see the classes are 0, 1, and 2. By multi-class, anything which has beyond binary is a multi-class problem. Like 0, 1, and 2, there are 3 labels, possible labels. So that's why it's a multi-class problem. And tree-based models give valuable insights in terms of, I mean, in terms of whether a feature is important or not, especially when the target is a multi-class classification problem. For binary classification, mutual information can help. For multi-class classification problem, like this kind of approach can help. Of course, there are other techniques also, but I think this is a very good technique which helps a lot. So what we are doing is we're looking at wine dataset. It has 178 rows and 13 features. The feature names are like this: 13 feature names like alcohol, malic acid, ash, and so on. And target variable is, I mean, based on these attributes, it is predicting some categories of alcohol, whether it is a whiskey, whether it is a rum or something. So based on this, like 0, 1, and 2, these are the 3 labels which are possible. Now, what we are doing is we are using a random forest classifier. I will tell you what is random forest maybe when we are talking about machine learning algorithms. But some machine learning algorithms are also used during feature importance. Like one of those is like this. So like for example, in previous class also we saw right in this RFE also we were using linear regression, right? It takes a model
Hmm.
into as a parameter. So sometimes machine learning algorithms are also used for feature engineering. So in this case, what we are saying is we have a random forest classifier. There is a decision tree classifier, and random forest classifier is actually an enhancement on decision tree. Why and how random forest is better than decision tree, I'll talk about that later on. But for the time being, there is a random forest classifier. It is a tree-based ensembled tree-based machine learning algorithm. So here what we are doing is any machine learning algorithm will take X and Y and learn a model, right? So based on our previous data, what is X? X is
Hmm.
the feature values and Y is the target. So there's a fit function in every model. You pass X and Y, it learns a model. Now only with this tree based models, not only random forest but also decision tree will give you model dot feature importance. Now what it is saying is how important each feature is Why? For making a prediction whether something is a some category of alcohol or not. So from this we can see that the alcohol block, which is this one, has the highest contribution, which is 0.13. No, I think there is 0.17 also somewhere. No. 0.15 is there. 16 is here. Okay. I think 16 is the highest one. Let me see. It is saying index number 12 is the highest one. So index number 12 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 14. No, top 5 feature is 12. This is the last one, 14. But 0.15 is also there as a feature importance, right? But let me check what it is showing here. No, it is saying 9th is the best feature. Okay. So now what is happening is, so 9th means this one. 9th is this one, 0.16. Now what happens is, during this random forest classifier itself also, you saw some results back then, and now you are seeing some other result. Like when I was running it was having some other. This is because this machine learning models are little random, right? So now this random forest classifier, if I look at it in scikit-learn, it must be having a parameter called random state. Let me check, does it have a random state or not? Random state, right? So it has a random state. So if I just pass a random state here, so see, now you saw this one is highest, right? If I just rerun it again, it see the numbers are changing, right? So how do you make sure that the numbers, because when you show it to someone, you try something, and when you are actually showing it, it is something else. So then it becomes a little difficult, right, to convey your thing. So at that time, you pass something called as a random state parameter to the algorithm, to a machine learning algorithm. Now it should likely produce the same results all the time. It is producing 0.17 here. It is producing 0.17 again, 0.17 again. I'm running multiple times. Okay, it is doing 0.17 all the time. So this is the use of this random state attribute of a machine learning model. It will make your results consistent, because when we are actually publishing any paper and all also, so at that time, so when we are publishing any papers or something, at that time also we have to mention what random state did we use, because they may want to examine and evaluate whether what you have done is correct or not, right? So there you have to pass this random state function attribute, so that your results are always constant. Now here you see that what it is saying is this. Yeah. Yes.
So for random state, we will always keep the number as 24.
No, you can keep any number. It is like any number, but see, if we change the number, the result will change. Okay, so see, it got changed, right? But if you keep the number same, it will always be constant if you don't change the number. So for your experiment, you decide some number and you put it here, and when you are showing it to anyone else, you use that number only.
Okay.
Okay, so it can be any number. It is not a fixed number, but some number, anything that comes to your mind, which has to be a constant.
Okay.
Now why it happens is because internally, while learning the machine learning model, it's just some shuffling and all. Okay, now shuffling of the data and all. So now if this is a seed for that shuffle, so now if you change it, the shuffling will change, and based on the shuffling, the importance and all will also change, right? Now there may be a question that, okay, if the feature importance are continuously changing, how do I know which features are important, right?
Yeah.
So because if it is continuously changing, how do I know? So like this I used only for reproducibility. You may not use it. Why it is used essentially is so that if you have done some experiment and you want to show it to some larger community or something, at that time you must be able to reproduce your results. So for that this is used. But ideally, I mean, when you are doing it on your own experimenting, you don't need to put anything. Now you will say that, okay, it is changing. How do I know which one is better? See, it will change, But from this you will understand that okay, this one and this one are almost always having the higher numbers. Like see, it is 0.11, 0.12. I'll run it again, 0.16, 0.12. So almost always these two features are high, right? Maybe numbers are changing slightly because of this thing. Now it is 0.18. See, you look at only the second feature, it will never be high. It will always be 0.02 to 0.04 at max.
Hmm.
See, so essentially this gives you a very good feel on which features are important. It may not be very accurate, okay? It may not be absolutely accurate in the sense that it will always be 0.17, it will always be 0.15. That may not be true, but it will at a high level give you an idea on which features are important, right? Now and of course, when the data scientist, when you're familiar with the data and whatever this algorithm is suggesting, you can also understand, okay, it is saying that for this proline, color diversity and alcohols are important. So and also in general, I think that this feature, which is alcohol and the proline, so these two are actually important while making an alcohol, I mean while deciding something is an alcohol or not. So that's why you see
Hmm.
that the same feature names are always changed same. So these two are the top features. The numbers will change, but always the features will be, this will be the top features only. Maybe 12 will become 9, 9 will become 6 and so on, but at least the top 5 will always stay the same most of the time. So maybe whatever is coming as rank 1 can come as rank 3. But ideally the top 5, if you are looking at, they should give you the same list of names. The order may vary a little. Okay, so this is a technique wherein what you are doing is you are learning a machine learning model on your data, and that machine learning model, so when you are actually learning a model, you may not use this classifier. This is only for understanding which features are important. Maybe after this
Okay.
I can use a deep learning model, or maybe some other multi-layer perceptron model or something which can do much better than this. What this is helping me do is helping me understand which features are important. So what we are doing
Hmm.
is we have learned the model. We are again arc sort. I told you last time. What it is doing is it is sorting this list based on index, and it is reversing that list. This -1 means reversal.
Hmm.
So this is actually the reversed list, which is saying 12, 6, 9 something, and here we are saying we are taking the we are slicing this first 5. So this is the 5 indices, and then again we are calling this data set feature names and passing the index to get the feature names. Okay. So this is a tree based technique of finding out feature importance, which is random forest classifier, using random forest classifier. And this is my recommended approach for anything that you start with. This is the first approach that you should look at while deciding feature importance or something. When the problem is of multi-class type. When it is of binary classification, mutual information is good. It is a binary classification, then mutual information is fine. When it is a multi-class classification problem, then you should look at tree-based. Even for regression also, you can look at tree-based kind of approach. I mean like random forest classification approach. Now, this is the last one, I guess. When the data set is very small, you have only 100 or 80 or 150 kind of a records. At that
Hmm.
time, you should look at sequential feature selection. Now, so here it helps you sequentially select feature. So we saw a recursive feature elimination. This is the opposite of recursive feature elimination. So there we had 10, and we are going down gradually from 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Here we are starting with 1 and we are adding 2, 3, 4, 5 until we see, I mean, based on the number of features that we want. Like for example, in this data set, we have only 4 features. Okay, 1, 2, 3, 4. But we still want to use only 2 features. I don't want to use 4 features, right? So here, again, this also uses a machine learning model like a KNN classifier, which is like K neighbor classifier, which is KNN, K nearest neighbor. So what we are saying is number of features you want to select. Here you will, let's say, which is 2. So what we are doing is we are calling a sequence feature. So this is actually not coming from, you have to remember, this is not coming from scikit-learn library. There is another library called MLextend. It is coming from MLextend library and feature selection package. It says that I mean there is a sequential feature selector class, and you pass any machine learning model to this, and you say how many features you want to select, and you say forward equal to true. So this, they have also given a way of doing a reverse. I mean reverse in the sense that you start from 10 and go backwards, but this algorithm is generally preferred in a forward direction, in the sense that you start with 0, take 1, take 2, take 3 until you reach how many features you want. I need 2 features, so it will start with 1, then it will do second, and it will stop there. Okay. Now what it is saying is, it is giving, I mean once you have learned this model using this feed function. So this feed function is essentially where all the magic happens in machine learning model. This is where the model is learned, right? And once the model is learned, you have k feature indices. So it will tell you all the feature indices, and it will and based on the feature names you can pass this index values to get the feature names. Like for example here, if I run, it is also okay. It is okay. It has done for the previous one. Okay. So now if you look at this, it is saying petal length and petal width. Okay. Now if we do for the other one also, let's say for alcohol, right? So I had for alcohol I had done this. So let's say on alcohol I run this algorithm. So what it is saying, alcohol and flavonoids are the two important features according to this technique, sequential feature selection. According to this technique, flavonoids and some other things, it doesn't, I mean flavonoids and alcohol are also there in the top 5 in this. So what it is saying, if you try multiple feature selection technique, what it does, it reinforces your confidence that okay, I am selecting the right features. Okay. So let's say you applied this technique and you applied this technique also, I mean this technique also, and both of them are giving similar kind of features as their important features. Then you understand that okay, 2 or 3 algorithms I have tried, all the algorithms are saying that okay, these features are important, so I should definitely keep these features in my data set. Okay.
Okay.
So like for example here we have 4, right? 1, 2, 3, 4. If I select as 2 and say this thing, petal length and petal width, it is saying are the highest ones. Okay. Now another technique which reinforce, I think one more approach, these are all the feature selection techniques. There is one important thing that I wanted to tell you. I told you that I will tell you in this session also, that I talked about mutual information, but I didn't. I had little bit brushed up on what is correlation, but we had not used correlation, right? So here I'll talk about correlation. What we are doing is, this is a data frame, right? So this is a data frame that that is there in this. I mean this is the Irish data set itself. So what I'm doing is I'm creating a data frame by passing the target variable and the columns name as data.feature names, right? And the column names, and I'm passing x and y, and there is a np.c underscore function where you can pass the xy. So essentially it was not a data frame. This one is actually an NP array that we are getting from this data variable, right? So where from this data is coming? This data is actually coming from uh, uh, this data is load y, where is the load iris, right? So there is a data sets inside scikit-learn which is using load iris. So this has x and y. This x and y are numpy arrays. These are not data frames. Okay. Now I need to convert it into data frame first by passing this. Once the data frame is there, I will call correlation df.coar. So now correlation can only happen if all the things are numbers. Here you will see everything x and y are all numbers. So you will see there is no, see everything is number and y is also a number. So you can do a correlationship among them. Now if you do a df.coar, what it is saying is sepal length is correlated with sepal length with a correlation of 1. As I told you last time also, correlationship 1 means positively correlated. If one is increasing, the other will increase. If one is decreasing, the other will decrease. Right? So sepal length and sepal length are the same feature, so they will completely overlap each other. So this will always be 1. Now sepal length to sepal width, it is minus 0.11. So it is saying that
Negative.
sepal length and sepal width are negatively correlated. It means if sepal length is increasing, sepal width will decrease, but they are very faintly correlated. I mean there is it is not like one is going minus 10, the other is going plus 10. Not like that, because it is minus 0.11. Very faintly correlated, negative direction, but faintly correlated. So it means that if let's say your length is increasing by 10, this will decrease by 1 or 2, something like that. Okay. Now if sepal length again has a very strong correlation with petal length. Now, if sepal length is increasing, your petal length will also increase and of the same magnitude, almost of the same magnitude. So, like for example, sepal length increases by 10 cm, then petal length will increase by 8 cm, nearly 8 cm or 9 cm it will increase, very close to this thing. Now, if you look at sepal length and petal width, it is also very closely correlated. It is, I mean, in the positive way, this increases, this will increase. Now, if we look at target is the classification, like this is 0 1 0 1, right, y value. So if this is increasing, this is also increase, and by a very good margin, like by 0.8. So that is why this is an important feature. Now if this is increasing, this is decreasing by minus 0.42. So this is not that high as 0.78. 0.42 is less. So minus and plus doesn't make a difference. What is important is this value. If the value is very high, then it means there is a very strong correlation. Like for example, you look at petal length and petal width with respect to target, they are 0.94 and 0.95, right? Very highly correlated. So if they are very highly correlated, these two features must be important. And also this technique also told us that petal length and petal width are very important features. Correlation is also
Hmm.
saying the same thing, that these two are highly correlated with the target. So all of them, most of this feature engineering approach that we talked about will give you the same results all the time. Correlationship is a very, as I told you, correlationship is a very good initial estimator whether something is correlated or not. But when they are not linearly correlated, this may not be very important. So correlation should give you a very good initial estimate whether something is correlated or not. But what proves, I mean, what are more sophisticated techniques are the ones that I talked about here. Like for example, random forest feature importance, mutual information, uh, RFE techniques. Dimension reduction is a different thing. It doesn't give you feature importance as such. It helps you reduce the dimension. It doesn't give you feature importance that much. But that is, I mean, it doesn't help you in reduce the number of, I mean, reduce the dimensionality of the feature, but it will never tell you which features are important. Like if you want to explain it to
Acha.
your client or something, in the sense that okay, my algorithm is predicting something as 1, something as 0, because these features are important. It is treating these features are very important, that is why it is predicting this thing. But in this case, if you are using PCA, you will never be able to explain it to anyone. You can say that okay, I have transformed the data, but you cannot say which feature, because of which feature the data got transformed to these things. So for, if you want to understand which features are important, I think these are the 4 techniques: mutual information, RFE, tree based, like random forest,
Rapa.
right, random forest, sequential feature, and correlation. These are the 5 techniques. Let's say. I think,
Okay.
yeah, yeah.
So when we so when we have to find the which features are important, then first we need to apply the feature engineering method and then do go for the dimensionality reduction, right?
No, no. See, yes, of course. First do feature engineering, then do dimensional reduction. But how it should be done in machine learning is that you should first, whatever data set is there, first you learn a model. First thing, you learn a model first. Once you learn a model, and if your accuracy is not coming out as very good, or the model is not doing, I mean, the model performance is not very good, then you come back to your drawing board and do all this feature engineering stuff. Okay, first feature engineering is not required initially. You
Acha.
have to first learn a model, and once you have learned a model and you see that the model is overfitting, and then okay, you understand, okay, it is overfitting, so maybe I have to reduce some features. If I reduce some features, maybe the overfitting
Okay.
will go away. So we will come back to this, but why I told you this at this stage is because you can remember, okay, there are some feature engineering techniques which are there which can help me reduce the number of features which are responsible for overfitting. So while learning a model, when we see in our subsequent sessions, when we see that okay, the model is overfitting, you should tell that okay, it looks like the model is overfitting, so can we try feature engineering? Okay.
Acha.
So, and your point is correct. You start always with feature importance and then you do dimensionality reduction if required.
Okay.
And
So it
dimensionality
means
reduction is
basically
essentially.
we not use the feature engineering or dimensionality reduction when we learn the model. First, we understand if the model is working fine, then we do not have to go for all these techniques.
Right, correct. Correct. But most of the
Acha.
time, this will not work. I mean, most of the times, the model doesn't work in the first go. But how
Uh-huh.
it should be, why it should be done in this way is because if you initially do feature engineering and remove some features, you may miss some of the important features also. Even if we are reducing
Right.
0.11 and all, like we are saying that okay, the feature importance is 0.00 something,
Mm.
so I am removing it. But you don't know, it may improve your accuracy a little bit also. So, I mean, so initially it should not be done. Why it is done in the reverse way is because so that you understand the problem, you can understand what the algorithm is doing. You yourself understand that okay, the model is underfitting or overfitting. If it is underfitting, you need to add feature. You cannot remove feature from there. So let's say you have already have very few features, 4 or 5 or 6 features, and there you have and your model is doing 70%. At that time, if you want to do reduce the number of features, the performance may go down further. So feature engineering will help only when you have a lot of features, let's say 10 or 20 features, and then you have learned a model is doing very good at training time, but on testing data set it is doing very poor, which is a overfitting case. In those
Mm.
situations you come back and reduce your features. Or like very simple cases, like for example in this you see, right, something is zero. If something is zero, that you can remove straight away. I mean, sometimes you can remove those kind of features, but those should be done later on. Like for example, once you have learned a model and you feel that the training is taking a lot of time, can I reduce some of my features? Or if you see that some features are unnecessarily garbage features which are making, I mean, like for example, like this feature, like which has zero feature important mutual information, right? So
Mm.
this feature will unnecessarily make the model more complex. So we want to do the same thing with less number of features. And like mutual information 0.000 till maybe till this itself, these many features are garbage features. These features you can remove straight
Right.
away. But ideally the way is you take a data, you acquire the data from different sources. We talked about data acquisition, how you can acquire data from different
Mm.
sources, scrape the web, collect data from web portals or something, create a data frame. Once you have the data frame, you do some data pre-processing. We talked about some pre-processing techniques also, like imputation, normalization, and so on.
Mm.
Once you have this data done, I mean data pre-processing, I mean data acquisition and the pre-processing done, you learn a model. Once the model is learned, you will get two things. You will get training accuracy, you will get testing accuracy. Now based on this training and testing accuracy, you will understand whether the model is overfitting or underfitting. If it is overfitting, you come back to feature engineering and do some feature engineering stuff and retry. If it is underfitting, you think of what other features you can add, because the model is not underfitting because it doesn't have enough data. Maybe a model can underfit because of two reasons. We'll talk about that mostly in the next session, a little bit on overfitting and underfitting, because these are very important concepts. Because if you understand overfitting and underfitting, I mean, that is the crux of machine learning. You, as a machine learning engineer, you need to understand when the model is overfitting. By looking at what data can you say that okay, the model is underfitting? By looking at what information can you say that the model is overfitting? So once you know underfitting or overfitting, then you know what to do. Like for example, in underfitting, if the model is underfitting, you need to add more data if less data is there, or you need to add more feature. These are the two options to overcome underfitting. Now, if the model is overfitting, what you can do, you can come back and reduce the number of features, or you can look at some other machine learning algorithms. Some machine learning algorithms will, or maybe you can shuffle the data a little bit so that the algorithm doesn't explicitly learn from the training, directly learn from the training. Also, there are some hyperparameters in the machine learning algorithms which you can change to avoid overfitting. So all these concepts we will learn in the subsequent classes. But till this, I think I mean, what we have covered is data acquisition, data pre-processing, and feature engineering. These three techniques we have done, and some little bit of exploratory data analysis like plotting and all. Right. So these all things
Okay.
we have to cover so far. Next, I think we will start with machine learning algorithms. And before that, I told you I will show you something that I need to prepare. That there is a very good library in Python, which essentially does a lot of EDA for you, like exploratory data analysis. You just give it a data set, tell that library that okay, this is my data set. It will do a lot of analysis. It will plot a lot of graphs and show you that okay, what is there in the data, what is missing, which data are correlated, which are uncorrelated, and so on. So those kind of report it will auto generate. So you don't have to write codes for them. So that I will explain in the next session, and then we will move to machine learning algorithm, regression and classifications.
Okay.
So that was that I
So
wanted to
for the
cover.
mutual information filter method, we always use the feature scikit-learn feature.
Yes, so
Can you?
most of the features are always coming from this thing, scikit-learn feature selection, right? So there is really a feature selection library. So if you look at
Uh,
scikit-learn feature selection, there inside this library, you will see many algorithms are there. Feature selection, okay. So univariate. So if you see, it is talking about univariate feature selection, recursive feature elimination. There is something missing. Sequential feature selection. So these are like some of the feature selection techniques that are there in scikit-learn. Not all of them are coming from feature selection. Like for example, this random forest classifier. This is coming from scikit-learn ensemble, right? So because it is a model itself. And I think this one is also coming from feature selection, right? Some of the techniques will come from feature selection, not all of them.
okay.
So whenever you want, I mean, whenever you have time, you can also read up these things. I mean, these are good documentations. I mean, I personally like the scikit-learn documentation. They give you very nice examples also. I mean, after explaining, they will give you some examples here which you can look at and understand. So you can take a look when you have time.
Okay.
Okay. Okay, that was all that I wanted to cover in this. We'll continue in the next session.
Uh, I have a question.
Tell me.
So at the very last, we have seen that there is a target feature